So, good afternoon, ladies and gentlemen. We are happy to have Professor Vladislav Mantič from the University of Sevilla in Spain as the speaker today, and he will speak about asymptotic solutions at the tip of interface cracks and multi-material forms with frictional contact and linear elasticity with anisotropic solids. So it's a long title, but Vlado is an expert in, say, computational mechanics, and so this is one of his key areas of research.
Thank you, Martin. Thanks to organizer of this seminar to give me this possibility to present you our work. This work will be done in collaboration with my previous PhD student, Maria Herrera and Alberto Barros. Not working. Okay. So, in the framework of linear elasticity, if we have material discontinuities or geometry discontinuities or boundary and interface condition in discontinuities, we can observe unbounded stresses or strain, and in these points or regions where material fusion can be initiated. For example, we have this very basic example of a reentrant corner, this also called V-notch, where we have traction-free faces. So we have at this stage, we have infinite stress in the framework of linear elasticity. If we have an example of so-called double-up joint, which is used, for example, in aeronautical industry, where is the joint between the laminum plate and composite material laminas. We have several multi-material corners here. For example, this is one, this is other one, these are the material corners. And in particular, this is a so-called closed corner or periodic corner, and this one we call like open corner. In this lamina, there is composite lamina, there is a crack which between two parts of lamina, and this can be if there is possibility of friction there. So this is the topic of this, also the topic of this talk, where we have in two faces of the crack, we have the frictional contact. There is the last example of a transverse crack in a 90-degree composite lamina, where we have this transverse crack, which is ending at the interface between 0 and 90-degree lamina. In all these cracks or corners, we have, as I mentioned previously, unbounded stresses in the framework of linear elasticity. It is another example of a crack terminating an interface. As I mentioned, at this, let's say, singular point, the fracture can initiate. Here we have a 3-point bending test, where a small crack can be formed at the tip of this V-notch. Or if we have a cutting tool, which is of course in frictional contact with the material being cut, a crack forms in the tip of this B-material corner. Here is another example of the material corner. This is the tip of this B-material corner. We have a wedge which is sliding in frictional contact over a substrate. These are the plots of isochromatic lines which characterize difference of principal stresses. And we see that at this point, using these photoelasticity images, we observe a kind of stress singularity, or in practical point of view, the stress concentration. And again, we can expect that for some loading, crack can appear there. But also in other configuration, for example, like this typical Hertzian contact in this region from -A to A. Here is the plot. This plot is the typical Hertzian pressure, and the solid line is the shear stress, which has stress concentration at the transition point between flip and stick contact zone. So there is no singularity interaction, but there is a stress concentration and evidently non-smooth behavior of the shear stress. So as you mentioned, at this singular point, typically at a crack tip or corner tip, can appear high stresses which can exceed material strengths, and the new crack can appear there. So there is an interest to characterize the asymptotic behavior of the solution of elliptic boundary value problems, which describe the formation and stress with solid in the neighborhood of these singular points. If we know the asymptotic behavior of the singular solution there, we can adopt measures to remove such singularity. We have published several work in this way, but also we can improve the accuracy of the computational codes like finite element or boundary element method using singular or enriched elements. But also we can check the accuracy of computational codes by comparing the solution with the predicted asymptotic behavior. So the overall objective of this work is to characterize the singular asymptotic behavior of the solution of linear elastic boundary value problems in anisotropic materials in presence of friction. The talk has two parts. In the first part, I will dedicate time to semi-analytical procedure to characterize the singular solution at the tip of an interface crack with frictional contact. And in the second part, I will talk about how to compute the singular solution in multi-material corners, which covered also the previous case, interface crack, but also many others. Both solutions I will present are semi-analytic. There are some classical results. If we consider the generalized plane strength, which we are considering on this talk, we consider three displacement in Cartesian coordinates as a function just of two Cartesian coordinates x1 and x2. So u1 and u1 are in plane displacement, and u3 is out of plane displacement. So there are some classical results by Kondratev and others that in the neighborhood of the singular point, the solution can be represented by the asymptotic series of power logarithmic terms in the radial coordinate and some angular function. In K and QL coefficients are called generalized stress intensity factor. Lambda n, the exponent is singularity exponent, which is eigenvalue of some nonlinear eigenvalue problem. G as a function of theta are singular angular shape function, we call them also eigenfunction. In the present work, we will consider the most simple situation where we consider just right boundaries of the wedges or corners, crack. We consider homogeneous boundary and interface condition, vanishing body forces in the neighborhood of the singular point. And in view of this assumption, we will also neglect the possibility to have logarithmic term, because in this under this assumption, this is just very rare and associated to multiple eigenvalues, algebraic multiplicity of eigenvalues. So in this situation, we have these two asymptotic expansion for displacement and stresses in the neighborhood of a singular point. Okay, I will briefly, I will briefly summarize. Okay, we are here. Okay, so we consider anisotropic constitutive law. This is the equation of equilibrium with the second order linear elliptic boundary equation, boundary value problem. Cij KL are is the positive definite tensor, symmetry positive definite tensor of elastic stiffnesses. And in the framework of the Strock formalism, which was developed in 1962 by Strock, we will consider this ansatz, the representation of the solution in displacement, just like a constant vector times a function, scalar function f of z variable, which is a combination, linear combination of coordinate x1 and x2. Where we use here like a factor number p. Okay, we will also introduce this dimensionless variable function of angle theta, zeta function. Okay, p is the number to be determined. If we substitute this expression, we will consider a particular expression for the function f of this power law form. If we substitute this in the equation of equilibrium, we get a quadratic eigenvalue problem, which surprisingly is a real quadratic eigenvalue problem, but the solution are complex number p, we call them complex eigenvalues, and the associated complex eigenvectors A. We can write this eigenvalue problem in this form, where U and D are quite relevant tensor in wave problem in solid mechanics. To solve this problem, we need to solve the stroke characteristic polynomial equation. It's a polynomial of the order 6, which has 3 pairs of complex conjugate values. We order them in the way the first 3 have positive imaginary part, and then associated 6 eigenvectors, which also arrange or order in this way. If we combine all these 6 eigenvalues and eigenvectors, we can obtain the general representation of any power law solution at near a singular point in displacement. Okay, where zeta alpha is this function, where p alpha is the complex eigenvalue. To compute stresses, we use the representation of stresses we had at the beginning, and we obtain, if we define the eigenvector B as a functional eigenvector A, just remind, these are the matrices Q and D, which are symmetric, and this is the non-symmetric matrix R. So in terms of these matrices given by the stiffness tensor, we get the 2 expression for the eigenvector B. We can compute 6 eigenvectors B alpha, which are again ordered in this way. So we obtain at the end this expression for the power law expression for stresses in the any anisotropic material in terms of radial coordinate and angular coordinate. And if we compute traction vector associated to a plane with this normal vector, which is basically a plane which contains the axis, 3 axes, and z-axis, we obtain this expression in, for traction in associated to the analogous expression in displacement. So it is possible if we define 3 times 3 matrices A and B, these are complex value matrices, which are defined by material parameters, elastic material parameters, and also 3 times 3 diagonal matrices Z and Z hat as a function of the dimensionless function of zeta 1, zeta 2, and zeta 3. We can obtain general power law expression for displacement and traction near any singular point in this form using this matrix, which is very convenient. We will use it in the next slide. So if you consider interface graph like in this plot to half planes, for example, this is a plot associated to the work by Continuum from 1977. So typically, if this situation or specimen is subjected to shear loading, in this situation, if this material is compliant and this is stiff, so very large contact zone usually appears in the neighborhood of this crack tip, and on the other side there is extremely small contact zone. Continuum actually show then theoretically at each crack tip there is a contact zone, but in this case it is of very extremely small length, and this can be half or even larger in comparison with the length of the crack. Okay? So if you look on this region near this crack tip point, we have this situation. So we can represent the situation near this interface crack tip that we have we can approximate by the semi-infinite crack with the contact zone, sliding frictional sliding contact zone along whole length of this infinite or semi-infinite crack. So this is basically the situation we will consider in the following analysis. So our objective is to generalize Comeniu contact model because Maria Comeniu did the analysis only for isotropic bimaterials and just the plane strain configuration. So we pretend to generalize this Comeniu model to an isotropic material under generalized plane strain. The novelty is that we will consider, like again, values, not only singularity exponent lambda, but also the angle of the friction shear vector omega, which is the direction of the shear vector a priori is not known. This is we adopted the procedure proposed by Chen in 2012. He studied the problem of two anisotropic wedges sliding over each other, and we adapted and generalized this procedure to the present problem of the interface crack, and we published just recently in the Journal of Mechanics and Physics of Solid. So we consider that in the vicinity of this interface edge, we have a semi-infinite crack located on the positive side of the x1 axis. On the negative x1, we have perfectly bonded material. A perfectly bonded material on the, let's say, left part, and frictional sliding contact on the right-hand part. The material 1 is the upper material, material 2 is the bottom material, and we will consider this subscript or superscript for the upper and lower material. If we firstly we need to impose the interface condition, which is basically equilibrium of traction along the crack faces, and also the equilibrium of traction along the perfectly bonded interface. If we use this expression, the second in 21, in this equilibrium condition, interface condition, we obtain this equation, and if we consider that these diagonal matrices very simple expression, they are basically identity matrix times a function e to the power of I lambda p. We obtain this expression, which can be arranged to this expression, and okay, this is one. And if we use the other condition for equilibrium of traction in the perfectly bonded part, we obtain this condition for this in this moment unknown vector q1, q1 half, q2, q2 half. Again, I remind that number 1 correspond to material 1, and number 2 here correspond to material. Additionally, we need to impose seniority contact condition of 0 relative displacement in the normal direction, which is basically this one. The x2 is perpendicular to the crack plane, interface plane. Additionally, we have Coulomb friction law. If we express the shear stress vector, we can decompose it into coordinates sigma 1 or 2 components sigma 1, 2 and sigma 3, 2. We can rewrite this Coulomb friction law in this form using omega angle, which is the angle of shear stress vector with respect to coordinate x. So we are arriving to this. This is from Coulomb friction law, and this is from seniority condition. Again, we can manage. We would need to simplify the system. We need to express, for example, q1 half, q2, and q2 half as a function of q1. Okay, so after some operation, we arrive to this expression, and additionally, we impose continuity of displacement in perfectly bonded part, which leads to this expression using the representation of displacement in the stroke formalism. So we end with this equation, which can be using the previous equation in 37 to be. It gives us the expression of q1 half in terms of q1, considering that this matrix invertible, which is usually the case. Now we have just like unknown the vector q1. finally, we have in total these three expressions from the interface condition we have. So at this moment, it is useful. Of course, it's relatively complicated, but you can see that some patterns repeat some matrices. So it is useful to simplify this system, this three equations we have obtained, to use impedance tensor introduced by Gebristen and mostly Barnett in the anisotropic elasticity theory, which is this matrix M1 or 2, depending on the material, and this and then use this impedance tensor to define the Hermitian positive definite matrix M star, okay, is the sum of inverses of the impedance matrices, and additionally. So first, in this way, we obtain this bimaterial matrix here appears, so the system is a bit more compact. And because these two equations are independent and relatively similar, we can introduce by a trick we can obtain this representation of this product, two matrices, square matrices, and this vector in this form, and substitute this to the first equation. This can be done if this matrix is invertible, which is the case for which is not the case for lambda 1/2 plus any integer number. I forgot to mention in the previous that that to be able to do this, we need to assume that lambda is not integer number. So at this moment, we consider all lambda which are not integer and also not half plus some integer number. These cases should be analyzed separately. I will not do it today because it would be a lot of let's say I will need a lot of time, but this can be done. So we will just focus on lambda which are not leading to non-invertible matrices in this analysis. So at this moment, we need to introduce this matrix, and we define the characteristic matrix of the interface class with frictional contact. We call it M lambda, is it M hat, which is a function of lambda, and material properties is independent of the friction coefficient and independent of omega. Okay, this is the definition of this characteristic matrix of interface class with frictional contact, and of course it appears here. And if we plug to this equation, we arrive to this final equation. Basically, because of this vector, we obtain the first characteristic eigenequation for the singularity analysis of interface crack with sliding friction contact. So we can see here we have one eigenvalue, which is lambda, so for nonlinear eigenproblem, and another eigenvalue is omega. These are lambda and omega are unknown. Mu is the friction coefficient, which is known, and also is known material properties, which are defining this characteristic matrix M hat. It is easy to see because of the definition of this matrix M hat. That is a periodic function of lambda with period 1. So if lambda is solving this equation, of lambda plus n is also where n is integer number, is also solving this eigenequation. But we have two unknowns, so we need another eigenequation. So let's go, and we need to use the condition for relative this tangential displacement in the frictional sliding part of the interface, basically in the crack. Okay, so because we consider isotropic friction low, so the relative displacement should be opposite to the shear vector in order to fulfill collinearity and also dissipation condition. So in this way, we have that omega u is basically omega plus or minus b, and in this way we can write this condition for relation of delta u3 and delta u1, the relative displacement between the crack faces, and because of the periodicity of function tangent, we can write this condition in this way. So now what we do, we will recover this expression from the power law expression from Strauss formalism. We substitute in these conditions, in this first we compute delta I1 is this. We have this simple expression because of the values of the zeta diagonal functions. Similarly, we arrive to this expression. Okay, now this long lengthy calculation, but quite trivial once we do it similarly like in the previous case. And also we can compute delta U3 in this form. And now we substitute in the previous condition we obtained, and we get the second characteristic eigenequation for this interface cut. So we have two eigenequations in terms of the elements of the characteristic matrix and hat, which is a periodic function of lambda, of singularity exponent lambda. So we can conclude that if we have one eigenvalue, one singularity exponent lambda, so if we assume any integer number, it will be also eigenvalue of this problem. Let's show some numerical examples. There is some question. No? So let's show some numerical example. We solve this equation, these two equations, these two unknown, they are nonlinear, and we use Lavender-Marquardt method to solve these two equations with high accuracy. We consider in this case like orthotropic material, which correspond to the unidirectional composite lamina, which are rotated different angles around. Sorry. Around axis 2. So we have initially like two composite lamina with fibers which are parallel, and then we rotate them some angle. Here we rotate it 45 in minus 60. These are material properties, and we obtain minus 45, and the other angle is changing. The material in the bottom, so this is 45, and the other lamina is rotating, and we are looking how this singularity exponent is changing. We consider the friction coefficient equal to 1. So this is the angle P2, which is the gives our orientation or rotation of the bottom lamina, and the upper lamina, top lamina is fixed. This is 1/2, which basically correspond to the classical singularity in cracks. Over 1/2, we have lambda, which corresponds to weak singularities, and below 1/2, we have singularities which are so-called strong singularities. We can show in our calculations that dissipation condition is fulfilled only by frictional dissipation condition is fulfilled just for lambda higher or equal to higher than 1/2. This is how the angle of the shear stress vector is changing when we rotate the lower lamina. Okay, you see for different singularity exponent, the color is the same. You can see how it is changing. You can observe that for eigenvalues which are not 1/2, the difference between the shear vector orientation is 90 degrees, and also we have observed that it is independent. This angle, shear stress vector angle, are independent of the friction coefficient. It's curious because we don't see it in the equation, but we have observed it in our numerical solution. And the difference between angles of the solution corresponding to 1/2 is 180 degrees. Here you can see the effect of the friction coefficient on the singularity exponent lambda is for mu equal to 0.2, 0.5, 0.8, and 1. So we see that if we increase the friction coefficient, let's say the variations of the singularity exponent are increasing, no? But the shape is the same. But the amplitude of this variation is increasing with the value of the friction coefficient. Of course, we can, because we have analytical expressions for displacement and traction, so you can see here as a function for some particular orientation 30 degrees and minus 60 degrees, we can see how the displacement values are changing if with respect to polar angle theta. We observe that this is the angle theta, which corresponds to the crack, interface crack. So displacement are discontinuous. The tangential displacement are discontinuous, but the normal displacement is continuous. While tractions are continuous, but non-smooth at the interface crack, and they are also continuous at the bonded part. Well, this was the first part of my talk. In the second part, I will talk about the analysis of singularities multi-material corner configurations. This is, of course, much more, let's say, urgent work analysis because it tries to cover many situations. Between them, also the interface crack we have just studied, and many boundary conditions. So it is more complex, so I will not pretend explain you in all details, but just you can have some feeling about how we do it. In this case, we are also developing a semi-analytical procedure, which provides us arbitrary accuracy, if you like. But of course, we will also use stroke formalism, but a bit in different way. Stroke formalism is basically the formalism which gives us the way how to compute solution in anisotropic materials under generalized plane strain situation, which we call 2.5 dimension, which is something between 2D and 3D. Okay, so we consider in general a multi-material corner with any number of wedges, single material wedges, which can be bonded between them. The same color correspond to single material wedges, which are perfectly bonded between them, and different colors correspond to situation where at the interface we can have frictionless sliding or frictional sliding. So we can have situation like this, single material open corner, or multi-material open corner, or closed to periodic corner, which is single material with some specific interface condition, or multi-material closed corner. We will consider again power type singular solution for displacement and stresses under singularity exponent. We consider possibility of boundary interface condition for friction with this form of the Coulomb friction law. We consider here is like isotropic friction, although theories developed for anisotropic friction model, which is you can have an isotropic material, but using isotropic friction model, but in some situation you maybe need an isotropic friction model where we don't have, let's say, parallel shear stress vector and relative displacement vector in the contact zone. So theory is prepared more general, but our code, because we haven't done there's no demand at the moment, general code we developed is just for isotropic friction model. Well, the key ingredients of our development is the stroke formalism. You more or less know it. I will still revise it a bit. The things transfer matrix, which allows us in the considering power law solution, know the solution in the other part of some wedge. If you know solution in one part, one edge of the wedge, to know the solution of on the other part, it's quite easy, as you will see. And the matrix formalism for homogeneous and frictional boundary interface conditions I developed in my previous works. So we will consider boundary condition homogeneous. We call it orthogonal boundary condition because the traction vector and displacement vector are perpendicular to each other. Typically, either UI or TI is zero. It allows us to model classical Dirichlet-Neumann boundary condition, but also frictional sliding symmetry, anti-symmetry, and other boundary conditions. But in any case, we have the scalar product of stress vector and displacement vector is zero. We also consider anisotropic frictional sliding. So we have like boundary condition. We have the condition for normal displacement is zero. We have anisotropic friction law. We consider that the displacement sliding displacement vector can have different orientation than shear stress vector, but the dissipation condition should be fulfilled, and also condition for compression. For interface condition, we consider either perfect bonding between the wedges. Okay, so we have continuity of displacement and equilibrium of traction, or we consider frictional sliding. So we have continuity of normal displacement and equilibrium of traction, or an isotropic frictional sliding where we have continuity of normal displacement, equilibrium of tractions, and we have Coulomb friction law, we have compressibility equation, we have some sliding law, and also dissipation condition for this. Some quick review of the stroke formalism, which was basically developed at the end of 50s, but there were some previous very closely related works by Lekinski and Escher. So we already saw this, that we express displacement in terms of one constant vector times one scalar function of zeta variable. We already know that this P will be complex. We arrived to this quadratic eigenvalue problem, we know it. But now we will don't work with traction directly, it's preferable. This was the genius idea by Stroh to use stress function vector, which is related to stresses in terms of derivatives. Okay, so the stress function vector phi is of the same order like U, and this allows us to work with displacement and stress function vector together in one sixth variable of the sixth order. But sorry, U vector is given in terms of eigenvectors A, and phi stress function vector is given in terms of eigenvectors, and they conjugate D. So this allows us to treat this U and phi together. So we define this vector W as this sixth order vector. We organize matrices A and B, and they conjugate is this 6 times 6 matrix, complex matrix X. And also we will work with this 6th order diagonal matrix Z. So using this power law expression for function F, we have this power law expression for W vector, which combines both displacement and stress function vector. If we consider one single material wedge, we have this expression for W in one angle, in the other angle. If we compute from here this constant vector T by inverting this matrix, which is invertible, so we obtain this transfer matrix proposed by Tim in 1997. This matrix E1 for the material 1. Okay, so this allows us to compute. If we know W here, we automatically know W here. But because of continuity of continuity condition, if these two wedges are perfectly bonded, we have this continuity condition for W. So we already know, using the similar procedure, W along the other edge, and then another edge, other edge, other edge. So we just need to know W here, and we know W, which gives displacement and stress function vector in the whole, this multi-material wedge, edge or wedge, sorry, or corner, with perfectly bonded interfaces. Because of the complexity to explain our theory in multi-material corner, I will explain just for two materials, which can be perfectly bonded or with friction or legs or frictional interface. Okay, this is the open corner. If theta 2 and theta 0 coincide, we can have closed corner, and we can have perfect bonding of friction with sliding. I will not explain too much about anisotropic friction because we haven't developed still the code, but the theoretical development perfectly allows to consider anisotropic friction. I will just move directly to definition of local Cartesian coordinate system to be able to write this boundary condition and interface conditions in a linear fashion. We need to introduce this local coordinate system on each face or interface. These are standard coordinate system in let's say cylindrical coordinates, N is the normal vector to the face, SR is in the radial direction, in S3 in the X3 direction. Because of friction, we need to introduce also vector K, which is the direction of friction shear stress vector in a plane or in the face or interface. And also in the plane K and N, we introduce another vectors mu and S mu. Vector mu is the direction of the traction vector in frictionless contact. We consider this mu is the friction coefficient, and this is the traction vector, easily to see. Then we define a mu unit vector in this way. This will be fundamental to develop everything in the simple form using this standard vector. This local coordinate system are fundamental for the further development. For homogeneous boundary condition, we are able to, using these coordinate vectors, different coordinate system, we can consider all these boundary conditions: free, fixed, symmetry, anti-symmetry, and restricting or allowing only some of this displacement. And we define these matrices du and the kind of d phi in this way using these unit vectors. So we can write any of these homogeneous boundary conditions in this form, okay? And this interesting and useful that du and d phi fulfill this orthogonality condition and allows us to form these 6 times 6 real matrices of these boundary condition matrices, which are also orthogonal. So this is the orthogonal matrix, easy to show. If we consider boundary condition of frictional sliding, we can also write it like a linear condition where omega is unknown, the vector of the shear stress vector in the contact zone is a priori unknown. But the trick is that these matrices now are not square, they are rectangular matrices, but we can design or devise adjoint matrices of smaller order that at the end we can form this main boundary condition matrix 6 times 6, which is also orthogonal. So in this way, we have in both cases, in homogeneous boundary condition or friction contact boundary condition, these 6 times 6 matrix boundary condition matrices, which are orthogonal. So this allows us to write the boundary condition in this form. dBc times W gives us, let's say, values of prescribed values of W or unknown values of W. Prescribed values are 0 and unknown values are to be determined. It is written for also for these are dimensions for each case: boundary condition, homogeneous boundary condition, or friction sliding condition. Because of orthogonality of dBc, we can multiply this relation by this dBc transpose, and we can compute W as a function of just unknown values of W using these matrices. In a similar way, we can work with interface condition. I don't go to all details, but we are considering perfect bonding or frictionless bonding, and we can write this condition like this linear condition using these matrices, using again these unit vectors in these local reference frames, and we can again form this main interface condition matrix, which is also again orthogonal, and we can do the same for frictional sliding, but of course matrices are more complex. But we end up again with the 12 times 12 matrix of this boundary formed by this boundary condition matrices, which is again orthogonal. So in both cases, for the we have formed these boundary condition matrices, interface condition matrices, which are which are 12 times 12, which are orthogonal. And again, we can proceed. We multiply these interface condition matrices by value of W from both sides of the interface. We obtain prescribed values, and if we multiply this equation by the transport of this interface condition matrix, we end up again with the expression which involves only unknown value of W. I will skip this. So continuing, if we use this 2 times, use this transfer matrix expression by thing, but we rewrite it in this form, and we can collect this expression for the bimaterial corner in this form. This is the matrix 12 times 24, which forms kind of this K corner extended matrix, and this vector W for the bimaterial corner is here. And if the corner is open, we can organize all these boundary condition matrices and interface condition matrices in this matrix, in block matrix, which is also again orthogonal. These are these unknown values of V W. These are let's say the full vector of W. And this is the procedure how we end up in the end with this matrix for the open bimaterial corner. This matrix K is given as matrix of analytical functions. It involves material parameter, boundary, and interface condition. F is the number of boundary or interface condition in restriction. If we have just one, for example, interface frictional condition, so F is 1. If we have both boundary condition and interface boundary condition, frictional contact, so F is 3. So this matrix can be rectangular if we have frictional contact condition. Similarly, we proceed for the closed corner. I will skip this because it's very, very similar. Just matrices are a bit organized in different ways. So at the end, we have finished, we have ended up with this, let's say, eigen system, where we have K corner matrix, which is function of lambda and omega. We can have 1 omega if we have 1 contact zone, or up to 3 in this bimaterial corner. So omega has dimension F, capital F, 1, 2, or 3 in this case. So this is homogeneous linear system. To solve it, we are looking for non-trivial solution. So if we have frictional conditions, so the rank of this matrix is 12 minus F. And we are looking for non-trivial solutions. So if we have no frictional condition, we look for determinant of K corner equal to 0. This is, let's say, quite standard way how to proceed. But if we have frictional conditions, so we have rectangular matrix, and we need to decrease the rank of this matrix. So we have overdetermined the homogeneous linear system. So we need to look for the minimum singular value. For this view, we use singular value decomposition for this matrix, and we look for the, let's say, sigma 1 or sigma minimum equal to 0. This is characteristic equation in this problem. So I will show a few examples. This is the double lap joint. We can see several multi-material corners in this double lap joint. We saw like an example at the beginning. We consider this corner, which is, let's say, this one. We have, let's say, rectangular corner. This is the composite lamina, and this is adhesive. And we look for singularity exponents there. And we have here a real part. These are a real lambda. There are no complex lambda. And these are, let's say, the singularity exponents we have found with our code using, let's say, just this determinant condition. However, if there is a crack here, so we can consider frictional contact in this crack. And we need to look for the minimum singular value of this rectangular matrix. So what we do a plot of this singular value sigma 1 and look for minima which should be 0. Okay, so we look for minima value, which are these values with red wine color, and this eigenvalues which fulfill dissipation condition, frictional dissipation condition for energy. Okay, so this is basically we have a laminate, then we have adhesive, and this laminate can be rotated. So we consider two cases with phi equal to 0 or phi equal to 40. It's very surprising that even if we have like symmetry in the plane x1, x2, we have non-symmetric solution. Okay? I was first time surprised when I computed this. There are some values of omega which are about 80 degrees, which are not absolutely not expected. Nobody expected it. Everybody computed up to that time omega 0, 90, or 180. But we have symmetric problem, but the solution is non-symmetric. Okay? And this we have shown recently today, this year published article that this is possible because of in 3D this Coulomb cone is let's say nonlinear. This leads to the possibility that non-symmetric eigensolution appear. Because there is a general code for multimaterial corners is able also to solve the problem of an interface crack with friction. So we compared these two approaches I showed today. This is the solution of these two eigenequations. Each line, the blue color and the green one, are let's say loci of where one eigenequation vanishes is 0, and in the cross point we have solution. The red points correspond to values of singularity exponent lambda different from 1/2, and green one correspond to the singularity exponent equal to 1/2. And this is, if you look on the plot for the sigma 1, I mean minimum singular value of this k-corner matrix, 12 times 12 minus 1 in this case. And again, we see that we obtain perfect agreement with these red points and green points. We found like 0 values or 0 minimum singular value of this K matrix. If we compare our code with previously developed code in published literature, you can see that if you look, all of them are focused on a singular multimaterial material. Some of them are not able to solve anisotropic problems. Some of them have limited variability of boundary condition or interface condition they consider. But some of them are just for plane problems. So this is our code is able to, let's say, to solve to have these characteristics. It's a very general boundary and interface condition. It's for anisotropic materials, any number of single material wedges in the corner, and it's 2.5D as we consider generalized plane strain. I will skip this conclusion. Basically, I will just would like to present you our online application where this code for multi-material corner is able. You can use it even now, and I will briefly introduce it. This code, it allows you to solve this eigenvalue problem, as I explained you here, without or restriction with any number of single material wedges in a corner with different interface condition, perfect bonding, frictionless sliding, and frictional sliding. We provide you with some video tutorial how to use our code. How you can go to the application. It's a very interactively, very friendly interface. You can even make mistakes. You will say that you are doing something which is not possible, etc. It informs you about the corner you are forming, defining, and at the end you need to insert or input the your email, and the problem is sent to our cluster, and at the end you should receive email with the solution. I mean, with values of singularity exponent lambda. If you include frictional contacts, so also angles for the frictional shear stress, And also the variation of displacement and stresses in the neighborhood of the corner tip. You can find there also some presentation of this code and the main references. The code was, this online application is described, and also works where the theoretical background and the test studies were published. We have carried out about 1,000 tests, compared with almost all problems were solved in literature about different problems in different number of materials, boundary condition, interface condition, and we obtain always perfect agreement. So I have showed you what first specific semi-analytic procedure to obtain the terms in the asymptotic expansion in the neighborhood of the tip of the interface crack with frictional sliding contact for any kind of anisotropic material and under generalized plane strain. Then I show you a general semi-analytical procedure to determine the asymptotic expansion, the term of asymptotic expansion in multi-material corners, with very variability for boundary and interface condition. Both procedures use stroformalism, lead to nonlinear eigenproblem. Of course, the first one is much simpler, but we obtain a very good agreement between both. And I show you some application of this procedure to interesting example. And at the end, I show you the single solve our online application for solving this kind of problems. Thank you for your attention.